Chapter 9, Free Convection. Convection is a heat transfer process between a solid surface and moving fluid. It is classified as a forced convection and a free convection. In forced convection, the flow is forced over the solid surface by external means, like a fan, a pump, or the blowing wind. It was well studied in Chapter 6, 7, and 8. In free convection, the flow is induced by buoyancy forces. It will be studied in Chapter 9. A. Buoyancy force and free convection. First, this is our system with hot vertical surface in contact with cold fluid at rest. We define this fluid particle as our control volume with two forces acting on it. One is a buoyancy force, the other is weight. Therefore, the net vertical force is buoyancy against weight. Second, if the fluid is heated, its density is decreased. Therefore, the fluid becomes lighter. As a result, buoyancy force is greater than the weight. Therefore, the fluid moves up. On the other hand, if the fluid is cooled, its density is increased. Therefore, the fluid becomes heavier. As a result, the buoyancy force is less than the weight. Therefore, the fluid moves down. As you can see, this kind of fluid motion is driven by the buoyancy force. Therefore, free convection is between the solid surface and buoyancy-induced moving fluid. Third, free convection, just like the forced convection, is classified as external and internal. In external free convection, the moving fluid is passing over the solid surface. In internal free convection, the flow is completely confined by the solid surface. B. Difference between forced convection and free convection. First, this is a forced convection between solid surface and moving fluid. This is free convection between solid surface and buoyancy-induced moving fluid. The convection heat rate is determined by the Newton's cooling law, and it is represented in equation 1. Second, in order to get convection heat rate, we need to use equation 2 to find convection heat transfer coefficient H. Third, in order to get H, we need to find Newton's number equation. In forced convection, the Newton's number is a function of Rayleigh number, which is defined in equation 3, and Prandtl number. By comparison between flow Rayleigh number and critical Rayleigh number, the flow pattern is determined of being laminar or turbulent. In free convection, the Newton's number is a function of Rayleigh number, which is defined in equation 5, and Prandtl number. By comparison between flow Rayleigh number and critical Rayleigh number, the flow pattern is determinant of being laminar or turbulent. What is Rayleigh number? C. Define Rayleigh number and Grashof number. First, Rayleigh number Ra is defined in equation 1, where Lc is the characteristic length of the solid surface. Delta T is the temperature difference. G is a gravitational acceleration constant. Mu is kinematic viscosity of fluid. Alpha is the thermal diffusivity of the fluid. Beta is the thermal expansion coefficient of the fluid. Mathematically, it is defined in equation 2 with unit 1/Kelvin. In application for ideal gas fluid, equation 3 is used to calculate beta. For liquid fluid, beta is read from tables. Second, Grashof number, GR, is defined in equation 4. The only difference between Rayleigh number and Grashof number is this is alpha, this is mu. Grashof number is a good indicator of which forces will be dominant in a buoyancy-induced flow. Buoyancy force or friction force. Third, Rayleigh number is a product of Grashof number and Prandtl number. If Rayleigh number is large, like 10,000, heat transfer between the solid surface and the fluid is free convection. If the Rayleigh number is small, like 10, the heat transfer between the solid surface and the fluid is primarily conduction. The example 9-1 have to evaluate Rayleigh number. Air property mu, alpha, G are given. A. There's a hot plate with length L and a temperature Ts vertically placed in stationary air at T infinity. This results in external free convection between the plate and the buoyancy-induced moving air. Equation 1 defines the Rayleigh number, where Lc is the length L, delta T is between the solid surface plate and the moving fluid air Ts. Beta is calculated from the plate temperature and air temperature. B. There's a heated pipe with diameter D and temperature Ts placed in stationary air at T infinity. This results in external free convection between the pipe surface and induced moving air. Equation 3 defines the Rayleigh number, where Lc is the diameter, delta T is the temperature difference between the pipe surface and moving air. Beta is calculated from the solid surface temperature and air temperature. C. There's air maintained in a gap of delta with the two surfaces at a temperature T1 and T2. This results in internal free convection because the flow is induced by the buoyancy. Equation 5 defines the Rayleigh number, where LC is the gap delta. Delta T is the temperature difference between these two surfaces. Beta is calculated from the temperature T1 and T2. E. Free convection application of vertical enclosure. First, this is a vertical enclosure filled with gas with length L, width W, and height H. It is represent the dual pane window filled with gas like air. Second, the heat transfer mode within the enclosure is free convection between the solid surface and the moving fluid, because this flow is induced by the buoyancy and radiation between these two solid surfaces at different temperature. Third, the convection heat rate, Q, is defined in equation 1, where A is the surface area perpendicular to the convection heat flow. H is calculated from equation 2, where LC is the length L, and this is the temperature difference between the two surfaces. Fourth, for free convection in this vertical enclosure, Newton's number is a function of a Rayleigh number, which is defined in equation 3, and a Prandtl number, as well as the aspect ratio H over L. There are 4 Newton's number equations, A, B, C, D, depends upon the aspect ratio H over L range, Prandtl number range, and Rayleigh number range. F. Example 9-2, free convection application. There's a vertical dual pane window with a height of H, width of W, and a gap of L. It is filled with air to separate 2 window glasses. The window glass temperature is T1 and T2. We need to find the convection heat rate through the window. Air property, mu alpha, Prandtl number, and conductivity are provided. That's what we know and what we need to find out. Step 2, identify all the heat transfer mode. Due to buoyancy induced flow motion, there's free convection between the solid surface and a moving fluid. There's a radiation between these two solid surfaces. Step 3, select the proper equation. 1, to calculate convection heat rate. we plug in numbers to equation 1. A, T1, T2. So step 4, the rest of the work is to get the average heat transfer coefficient value, then Q convection. 1. For free convection in this vertical enclosure, Newton's number is a function of a Rayleigh number, Prandtl number, and aspect ratio H/L. We know Prandtl number, we calculate H/L and use equation 2 and 3 to calculate Rayleigh number, beta, G, T1, T2, L to the power 3, mu, alpha, to get Rayleigh number. 2. Select Newton's equation based on Prandtl number, aspect ratio, and Rayleigh number. We select the equation D for Newton's number equation because equation A and B only for small aspect ratio. Equation C is for larger Rayleigh number. Next, we plug in numbers to equation D to get its Newton number value. 3. We plug in numbers to equation 3, Newton number, thermal conductivity, L, to get its heat transfer coefficient value. Then plug back in numbers to equation 1, area, heat transfer coefficient, T1 minus T2, to get its convection heat rate. At this point, have you ever wondered for heat transfer system, is it possible to have both forced and free convection? The answer is a yes. G, mixed convection. Have to find Newton's number equation and then heat transfer coefficient. First, mixed convection is a heat transfer process where both forced convection and free convection coexist. For example, A is free convection because there's a reason air induced by the buoyancy around the hot cylinder. B is forced convection because it is between the solid hot surface and moving fluid blown by the fan. If buoyancy induced reason air around the hot cylinder and the blowing air by the fan coexist, C is a mixed convection. Second, if the convection is mixed, have to find Newton's number and then heat transfer coefficient. First, you need to determine which convection is dominant. Grashof number and Rayleigh number are defined in equation 1 and 2 respectively. We compare Grashof number with Rayleigh number square. If the ratio is much less than 1, like a 0.1, the forced convection is dominant. You can treat it as a forced convection problem. If the ratio is much greater than 1, like 10, free convection is dominant. Then you treat it as a free convection problem. However, if the ratio is close to 1, both convection are important. Then the mixed convection Nuss number is calculated from equation 5, where this is the forced convection, this is the free convection. The power n and the positive or negative sign is determined by whether these two flows assisting to each other or opposing to each other or converge to each other. At this point, we complete chapter 9 with this beautiful summary and outcomes on concepts, variables, scales, and equations. We end chapter 9.